Ghosal. And it's a paper that we'll post in a few days, so you're getting a sneak preview. There are two goals in this talk. The first is the mathematical goal, it's the concrete goal. So it's to construct something, in particular to construct the ASEP speed process. And I'll tell you what that means. But in kind of short terms, what it's going to mean is that I'm going to look at a second class particle started at the origin in ASEP. I'll tell you what all that means, with all particles first class to the left and all zeros, all empty particles to the right. And then I'm going to look at the location. I'll call this xt, and I look at it at time t. And what I'll show is that a limit exists as t goes to infinity to a random variable. So an almost sure limit exists. And in fact, this random variable will have a uniform distribution. So this will be uniform on -1, 1. Okay, and so that'll be the main result. I'll explain it more concretely in a moment. Now, the broader picture that I want to illustrate is the rich interplay between two areas or two techniques. One which is probabilistic methods, so couplings in particular. And the other is integrable methods, so exact formulas. And really, what I can say is that without, with just one of these methods, I can't prove this result, and with just the other, I can't. And so it's only together that you can. And this is a common theme that's been showing up a lot in probability and in various contexts over the last few years, that you can gain a lot by combining these techniques. So I want to give you an explanation for what type of combinations go into this. Okay, so but let me explain the model and the results first. Try to do okay, so what is the asymmetric simple exclusion process? So what you have is a one-dimensional lattice, probably a familiar model to many people. And on that you have particles. Okay, and so I'm going to imagine starting with particles everywhere to the left of the origin. I'll call this the origin. I'll put a red particle, which will be called a second class particle. And everywhere to the right, I'll put holes. I'm going to label these by their class. So these are all first class, second class, and these I'll call infinity class. Now, the rules of the game are the following. So in continuous time, every particle jumps. So particles attempt left and right jumps. So at some exponential rates, so rate L and R rates. And the jump is achieved if the particles class is lower than that of the destinations. Okay. So for instance, if my first class particle here decides to jump to the right, well, it has a lower class, so it will take that jump. It'll supersede the priority of the second class particle, and so the two of them will switch. So the second class particle needs to defer, needs to switch orders. On the other hand, if a second class particle tries to jump into a spot with a first class particle, the jump is suppressed. It doesn't occur. Okay, so now we can look at the trajectory. I'll just kind of draw schematically. So maybe the first class, I'll think of this as time. So maybe the second class particle initially stays put, and then it jumps to the right. And then after some point, it jumps back, and maybe it jumps back. And it could be jumping of its own volition, or it could be jumping because it's being forced to by first class particles. And so it will continue maybe doing something along these lines. So I'm going to call the location xt is going to be this location of the second class particle. And for normalizations, I'll assume that the right jump rate exceeds the left one. And this means that the particles will tend to move away from the bulk that they start in, and that the difference between R and L I'll normalize to be 1. Okay, so this will keep a constant asymmetry, but I'll possibly have different speeds. So with that, I can tell you the main theorem. Okay, and then I'll give you a picture. So the main theorem is that, well, it's what I wrote before. So if I look at the limit as t goes to infinity of xt over t, so this is, of course, random. The trajectory the second class particle takes is random. But if I divide by t, it satisfies a law of large numbers, almost sure. But the limit that it converges to almost surely is itself random and distributed as uniform on -1, 1. So this is the picture by which to understand this. So on the left, this is actually in the case of TASEP. So TASEP is when L equals 0. So these pictures are representing that, but the same phenomena, well, as we prove, occurs for general L. So the blue particle on the left is taking some trajectory. It's being kind of knocked around. What you see behind it, and I'll explain a little bit more later, is really the sort of density of first class particles, right? Initially, you start with a high density, well, density 1 and density 0 here. And over time, you still have density 1 and density 0, but then you have this sort of rarefaction fan that transitions from high density to low density. And so what's happening in this picture is there's a direction which is being chosen. And if you take this and you simulate ASEP and you do that 1,000 times for different instances of the process, what's showing on the right is the trace of the second class particle. Each one is independent, but you see that, say if you take a cross section, the distribution is uniform between a -1 slope and a +1 slope. And well, okay, it's maybe not obvious it's uniform from the picture, but that's what the result is saying. So this is what we prove. Okay. Now, before going into the result more, let me just tell you a corollary of this. And feel free, to clarify, ask any questions. Is the result itself clear? It's a little bit hard to initially wrap your mind around, right? You're proving an almost sure limit, but to a random thing. It's kind of like in the much simpler context of a polya urn, where you prove an almost sure limit for the polya urn, the frequency ratio, but it's still to a limit, in fact, a beta limit.
Excuse me. So it's a little surprising that the limit does not depend on L and R.
I agree. I agree. It's surprising, but the reason why this is, and I'll explain the heuristic for this in just a little while, is because the hydrodynamic limit for ASEP doesn't depend on L and R, as long as L is strictly less than R. Okay. So I'll give you a very heuristic explanation. Obviously, the proof is going to require more than heuristics. Okay. So here's a nice corollary. So if instead, let me just go back to my initial picture. Let me put in another set of labels. So this one, I'm going to label particles now by classes that are indexed by the numbers in all integers, so not just first, second, and infinity. So I'll have the 0 class, 1 class, 2 class, 3, and in this direction, I'll take the classes to be decreasing. And in fact, if you think about it from the perspective of the second class particle that I had in my original picture, everyone to the left is of a lower class. So the second class particle, the particle that starts here, doesn't really distinguish between all the particles that started to the left, and similarly doesn't distinguish between all the particles that started to the right. So if I just project onto the motion of this particle that starts off at 0, it will be exactly the same. It won't really have any regards for this labeling. But I can, consider this expanded version of the model where I have all of these labels and look at the evolution of each particle individually. So let me now call xt0 to be the motion of the particle that started off at 0, and then, xt -2 would be the particle that started off at -2. And let me ask, how do these behave? And in fact, it's clear that each one is marginally identical up to a horizontal shift. So the corollary is the following. So for xtn representing the location of the class N particle in the configuration I described, we have the following. So I'm going to look at the limit t goes to infinity of x tn over n. In principle, I should take a little offset by n, but I'm fixed, if n is fixed, then that goes to 0 divided by t. So this limit exists almost surely for all n in the integers. So because we can take a countable union of, or countable intersection of these almost sure limits, we know that this is almost sure over all. And what you get, this n-indexed process, which is keeping track of the speeds of each of these particles, is what's called the ASEP speed process. Now, let me give you a picture. This is actually, again, for TASEP. I haven't had time to simulate this stuff for ASEP, so I'm just taking this out of a paper from about a decade ago that does and studies this for TASEP for L equals 0. But what's being shown here is the value of n. So here they're looking for the values of n between 1 and 500. So all the particles that started off at position 1 up to 500. And they're looking at the terminal velocity that those particles took. And that's what this u is. So it's something between 1 and -1. And what they prove is, well, okay, I should say as part of our result is that actually the law of un is going to obviously then be translationally invariant with these uniform -1,1 marginals. Okay, so that's just clear from the construction. And that's what you're seeing in this picture. It really looks the same if you shift horizontally. But what's kind of remarkable and has been studied for TASEP, but not so much for ASEP, and should be, is the structure that you see these sort of clusterings, different areas where actually a lot of particles decide to move in the same direction, almost exactly the same direction. So there's these convoys that are formed. And so there's a very interesting structure to this speed process that I'm not going to talk about, but is something that now that it's been constructed is certainly deserving of more study. Okay, so that's the result. Let me now move to tell you a little bit about the context, the previous work related to this. And then I'm going to explain to you why this result is at all plausible.
A question, can I ask a question before you do the previous work?
Yes.
The previous picture of that fan, does the speed process tell you something about statements you can make about the density, how that density of the fan evolves?
Well, so you mean this fan, this one?
No, I was thinking on the left.
Oh. So on the left, well, so the density of the fan is going to be determined by the hydrodynamic equation, and I'll describe that to you just in a moment. It's certainly related. It's actually, I would say, a significant refinement of understanding the hydrodynamic theory. Mm-hmm. But yeah, I'll tell you how this rarefaction fan is evolving. It's actually by the Invissid-Burgers equation. So it's a relatively well understood evolution. And but going from that to our results takes some work. Heuristically, I'll explain why, and then I'll explain how you actually do it.
Okay, thank you.
Okay.
Sorry, one other question. So like in principle, if you understood this ASEP speed, if you understand this ASEP speed process very well, would you be able to basically just study it and get out the results for the height function, like convergence to Tracy-Whittem distribution for the height function at 0 and stuff? Or is it like you need to scale differently to see that? No, so the speed process is in the hydrodynamic scaling. It's where you're scaling time and space in equal proportions. Okay. There should be results that say that if you look along the trajectory that a second-class particle takes, and you look at the fluctuations it takes, it's not exactly linear. So you ask, how do those fluctuations grow? Well, those should be related to the KPZ exponents. In fact, it should be a diffusive, a 2/3 exponent. And this has been shown actually in the case of starting in Bernoulli initial data and putting a second-class particle at the origin. If you look at the trajectory, you can show the super diffusivity with an exponent of 2/3. And that actually then
there are some identities that relate that back to the KPZ 1/3 exponent. This is something that has been studied for ASEP, but
Okay, thank you.
again, in the stationary initial data. For the step initial data, I don't think people have really studied the fluctuations around what we show now to be limiting linear trajectory. And I think that that's something that perhaps can be accessible with our techniques. Okay, so just to put things into context, this question about studying the second-class particle, well, second-class particles have been studied for a long time in various contexts, but let me focus on the context of the step initial data, putting one at the leading edge. The first people to study this were Ferrari and Kipnis. That's Pablo Ferrari, and they showed that if you look at this xt over t, they showed a weak limit that it converges in distribution to this uniform -1,1. And actually, the proof is very simple. I'm not going to give it now. It's basically you use two different couplings, one which is just kind of mimicry of the system, which is shifted by one, and the other is just the basic coupling. And you can show this pretty easily. But anyway, I'll give you an explanation for this, which is almost a proof. They also showed a slightly stronger result about if you look at two different times and you take them out and scale them kind of far away, in some proportionate scaling, that you have convergence of the difference of the velocities to zero in probability. But they weren't able to get an almost sure limit. The proof of the almost sure limit, so this going to a limit almost surely, this was given about a decade later by Mountford and Guiol. And I'm not going to explain their proof, but I will say that it was very much based on the fact that TASEP, which is this case where L equals 0, or particles only jump to the right, is in correspondence with something called exponential last passage percolation. And this is a very powerful correspondence because it allows you to write down variational formulas for TASEP, and then use results about last passage percolation, say concentration results and things of that sort. So when we move into the context of ASEP, this relation completely breaks, and so we'll need a very different method. Now, the Ferrari-Kipnis method actually still works when you look at, oh, sorry, I should say for TASEP, this was they constructed this speed process, which is really, it follows immediately from Mountford Guiol, but then they studied it, and properties. So this was the TASEP speed process, which is not necessarily this, it's going to be a different process. It has different relation. The asymmetry actually affects the limiting speed process, I believe. Okay, so Ferrari and Kipnis showed this. They didn't deal with but their method still works for the ASEP, improving the distributional limit. And then there's alternative method that's much more recent for showing this uniform -1,1 result that goes through some algebraic tools, what's called class position symmetry. Okay, so that's all I want to say about the previous work. But in light of the fact that, say, Ferrari-Kipnis's work still applies, this implies that actually, in order to prove our result, it suffices to show just that the limit exists. So the theorem that we really need to show is that this limit exists, right? Because we already know that the limit is converging distribution to something. So if the limit exists, almost surely it will need to equal this in distribution. Okay, so the question is, how do we proceed in doing that? And so what I'd like to tell you is well, for the outline of the rest of the talk first. So the plan is to do the following. So the first thing I'm going to explain is the ASEP hydrodynamic limit theory, or and this is going to be kind of a heuristic explanation. I'm not going to go into the details of what exactly has been proven, but this will give you a sense of, in this law of large numbers scale, in the shape, in this scaling in which we're looking at, how does the bulk of the system evolve? Now, using that understanding, I'll give you a heuristic explanation for why you have a uniform minus 1, 1, and also, well, part of the reason why you have an almost shear limit. And this, I should say, this will be very sketchy. This is very heuristic. And then what I'll turn to is trying to explain to you actually the proof, which needs other ideas. And I'll focus on the L equals 0 proof. And you say, well, okay, that result was already known. That's fine. It's a different proof, and it's a proof that actually then with a few additional ingredients, so plus some additional ingredients, gives the L bigger than 0. So this is TASEP, and this is ASEP. Okay, so I'll focus, because TASEP is just a little cleaner, I'll focus the proof on TASEP, and then I'll tell you exactly what you need in order to go up to ASEP, and hopefully at that point it will be clear that it should work. Okay, so what is the ASEP hydrodynamic theory? Well, the idea is really what we were looking at over in this picture, which is, initially you have a density. So here the density is 1, and here of particles, and here the density is 0. And then somehow there's some sort of smooth transition from having density 1 to having density 0 in terms of particles. I'm not drawing it very suggestively here, but let me explain to you what I mean in terms of this. So let's just give some notation. So let's call eta tx, call these the occupation variables. Let me just focus on normal ASEP with particles and holes. So forget about second class particles for the moment, just particles and holes. So call these occupation variables. So this is going to be equal to 1 if there's a particle at x at time t, and 0 otherwise. Now, imagine that I have some initial data for my process, eta naught. Okay, so this is going to be, I should think of eta naught as being an element of 0, 1 to the z, right? Okay, and now I'm going to look at it, but I'm going to scale horizontal space by epsilon inverse. So I'm going to look at position x over epsilon inverse. And I'm going to call that something, I'll call it rho, which will represent a sort of a microscopic density on the scale of epsilon inverse. Now, of course, this is something that's really picking up all the zeros and ones. So I really want to, when I'm talking about this object, I really want to be talking about kind of a slightly smoothed version of it. So let me imagine that as epsilon goes to 0, this converges as a process in x weakly to some function, maybe a deterministic function, rho naught. So what you should really have in mind is my sort of microscopic picture. I have particles and then holes. What that is going to do, and I'm going to look on an epsilon inverse scale. So I'll look some big region. I'm going to smush that down to order 1. So you have now lots of little empty spots and lots of little holes. And then I'm going to take epsilon to 0, and this will converge to basically a step function. The density will be 1 to the left and 0 to the right. That's, in my example, that's what the initial data is going to become. Now, I know how to evolve the initial data via, well, just via ASEP. So I call this now, I'm going to look at it at time t over epsilon and position x over epsilon. And in the same way, I'll declare that to be rho t x. Okay. So there's nothing on the left. It's a random evolution, it's a Markov process. So now I have a random, even if I started with something deterministic, I have a random rho epsilon tx. Now the claim is that this converges again as epsilon goes to 0 to actually a deterministic function rho tx, and actually that this whole picture commutes if what I put here is what's called the inviscid Burger's equation. And this is actually an ill-posed equation, so I need to specify something that's called the weak entropy solution. Okay, so if you haven't looked at this before, don't worry, I'll tell you what it is. And actually, this commutes not just at a single time, but it commutes this is true as a space-time process. So if I fix the initial data process, then the entire space-time process will, in the limit epsilon goes to 0, evolve according to this inviscid Burger's equation. So this Inviscid-Burgers equation is the following PDE.
Excuse me, is it obvious that the t and the x should be scaled in the same rate?
Well, it's just what I'm doing. I'm not sure what it means to be obvious. So the idea is really a law of large numbers. I'm looking on a scale in which things are going to be the same in both directions. You could look on scales in which you're scaling things differently, but then you might see something different.
Okay, because the reason I'm asking is we work on the diffusions. Usually the x and the t are different rate. Yes, t
Well,
is
that's
x.
true, right? But of course, the diffusion is you're tuning asymmetries to be very close to zero or exactly zero. So if you were to tune L and R to be equal to each other, then in order to see a hydrodynamic limit, you would need to look on a diffusive scale.
Okay.
But because we're assuming, I should be again clear, L is strictly bigger than R, and in fact, the other way around, R is strictly bigger than L, then I'm fine. Actually, the reason why I took R minus L to equal 1 is so that I don't need to put a factor of R minus L in front of stuff.
Okay, thank you.
So the equation that you get is well, it's in fact, I should say, if you tuned R minus L to be epsilon, and then you took the scaling in the manner that I'm describing, then you would actually end up with the viscous Burgers equation, and the viscosity term would be a remnant of the fact that you're near this balanced case. Okay, so this is the equation. I'll actually, if you've never seen this, I'll give you a heuristic proof of this equation in just a moment. So this is the equation. It's a conservation law, and the relevant initial data for what we're talking about is this. If you took the step initial data, that will correspond in terms of this to taking rho naught x to be just the indicator function that x is less than or equal to 0. Now, how do you solve this equation? Well, subject to these conditions, you solve it using the method of characteristics. Okay. Now, the characteristic velocity associated to this is what you do is you look at the flux, you look at the nonlinear function of rho inside of this derivative. So that function is, well, rho minus rho squared. And then you take the derivative of it. So you get 1 minus 2 rho. And that's what's called the characteristic velocity. And now the way that the theory for solving this equation works is you take at time 0, so this is time 0, time is progressing. You take the initial data, so it was 1 and then 0, and you plug it into the characteristic velocity. So rho is 1, corresponds to a characteristic, which is 1 minus 2 times 1. So in other words, the value of the speed of the characteristics coming out of here is minus 1. So now I just draw straight lines with slope minus 1. And well, when I had rho is 0, the characteristic velocity is positive 1. So now I draw straight lines in this direction. In between, you see there's this empty area, and the fact that we're dealing with the entropy solution means that you should fill this in with what's called a rarefaction fan. Of course, you need to justify this, and well, there's some work in making these sorts of justifications of this theory, but this is what is understood. And so this is, if you want to then read off the solution at a later time t, what you do is you look at the slopes of the characteristics crossing your location, and you invert this. You take the inverse of this characteristic map, and it gives you the value of rho. So what you'll see then is, well, here the value will still be 1, here it will be still 0, and then there'll be a transition between, at the edge of the rarefaction fan, between 1 and 0. And if you just think about it for a moment, you see that the transition will be linear. And that has to do with the fact that the characteristic velocity is linear. So if I look, say, at a later time t, my solution will have evolved to look like this, between minus t and t. Now, a natural question is why? Why is this the right, well, for instance, why is this the right equation? And then, of course, why do you make sense of it in this way? And let me just give you an explanation that starts you in the right direction. if you imagine looking at TASEP, ASEP, whichever, and you have a density which is locally rho, what is reasonable to expect and what is shown in various contexts is that the local density around you, the local configuration around you should be, so let's say around a location of density rho, you should see something that's approximately IID Bernoulli rho as the local environment. This is the local stationary measure. In fact, on the entire line, the stationary measure of density rho that's translational invariant for ASEP will be Bernoulli product measure rho. And this is a very nice property. And so you'll expect to see that locally as well. So if you kind of zoom in to some region, I've taken my epsilon to be very, very small. I zoom in and I look at kind of what the particle system looks like, then you expect to have kind of some number of particles and some number of holes, and it's according to this IID Bernoulli thing. Now, if that is in fact true, then you can ask, what is the rate at which particles, if I look in a region here versus a region next to it, what's the rate at which particle, the density changes? Well, particles move. So in order for a particle to move, I basically need to have a particle and then I need to have a hole. And under the Bernoulli measure, the probability of that is rho times 1 minus rho. So the rate at which particles move in this region will be rho times 1 minus rho. And the same is true in this region, except that the value, well, I have a slightly different value of rho there. So what I want to look at is the sort of net flow of density at a location, say between the two, will be determined by the spatial derivative of this flux function. And that's exactly what the hydrodynamic equation is saying. Okay. So that's a sort of a derivation of what this equation is saying. But let's for now just accept the equation. And what I want to explain to you is, accepting this notion of the hydrodynamic theory and also the local stationarity, which I should say we don't really appeal to. And the proof is heuristically based on this, but I'm not appealing to any particular theorem about it right here. Why do we have the result? Or at least why is it reasonable? So why, for instance, does the second-class particle attain a uniform 0-1 velocity? And so to justify that, I need to explain to you really another way of thinking about second-class particles, which is that second-class particles represent defects or differences between two different initial data. And so let me tell you how to understand that. So this is through what's called the basic coupling. Okay, so this is a very important idea in interacting particle system. So imagine that I want to imagine I want to simulate ASEP, and I want to save myself a little bit of time. I want to be able to simulate it for every initial data in such a way that marginally the evolution for any given one will be the correct Markov process. But I want to be efficient. So one way of doing that is to start at the beginning of the day and just, so think of this as time. Above every integer location, I draw a straight line, and then I draw, according to a Poisson point process of intensity L and R, I draw arrows that point to the left or point to the right. And I do this independently at every space-time, at every location. Okay, now what happens is when I think of running the system, maybe I put in 2 particles, the way that the particles evolve is, well, they evolve relative to this environment. So they just try to move forward and follow the arrows. So maybe there's an arrow there. Maybe it goes up. I guess it goes up and over. So this wasn't such an interesting picture because they don't really interact. This one goes up. I suppose if I had put in another particle here, let me imagine now what happened. So this one went up. It could go over. But now when it tries to go over, there's already a particle there. So it's actually forced to continue going up, and it makes its way over. So the basic coupling actually allows you to put all of the evolutions on a common probability space. And under the basic coupling, the second-class particles become defects in the following way. So let me explain why this is. And this is true because of the following property. This is what's called attractivity of the basic coupling. So the basic coupling is attractive in the following sense. So let me imagine starting two different initial data, eta naught and zeta naught. So which should be pointwise ordered. So in particular, I mean that for every j, this is true. Okay, so maybe what you want to have in mind is that the eta particles are the two particles I initially identified. So these are the eta particles. And then the zeta particle actually adds additionally. So it's this one plus these two. Okay, so they start off ordered pointwise. So if I start with that type of situation, so if this is true, then it will maintain that property. It'll be true pointwise under the basic coupling that this will happen. And in fact, more is true, that the number of, there'll be conservation of the number of particles. So the difference between these two, the 3-particle configuration and the 2-particle configuration will actually represent a 1-particle configuration. And so the evolution of this excess particle will be the second-class particle. Now, I'm not saying that the evolution that you're seeing here. What I mean is that the second, so if I look at the, so let me see. So if I look at the difference between eta t minus, zeta t minus eta t, this will be equal to the indicator function for the location. So let's say j, that xt is equal to j. So if xt is a second-class particle, so if I started out with 2 first-class particles at the black locations and a second-class particle at the blue location on the left, then the evolution of the second-class particle will be equal in distribution to this difference of the two configurations. So that's to justifying the notion of this microscopic difference. Okay, now that's useful because we can then think of, at the hydrodynamic level, taking the difference of different initial data as representing a sort of a scaling limit of the evolution of second-class particles. So
sorry, in this example you've drawn here, what is like eta naught of j and zeta naught of j again, or eta,
okay,
eta j and zeta j?
So the eta is just the location of these two particles in black, or I guess in blue now. So eta naught would be, these are occupation variables. These are zeros or ones. So it would be 0 everywhere except at these two locations. And then I look at the evolution of those occupation variables. So, they're 1 in locations, if I look at a later time, so it would be equal to 1 in this location and 1 in this location and 0 everywhere else. The zeta thing is the same, except now I'm looking at the evolution of 3 particles. So the difference between the zeta evolution and the eta evolution is going to be, well, I guess in the way I've drawn it is just going to be this evolution, this particle. But you can imagine situations where let's say that instead of this transition, let's say that this particle, actually there was an arrow that wanted to point it to the right. Okay, so maybe I didn't give such a good example. Let me redraw this. So now, so my initial particle, if I don't think about the particle all the way to the left, my initial particle can just go and follow to its heart's content and go to the right. Right, but now when I include 3 particles, that jump is excluded, right? So when I look at the 3-particle system, it's forced to go up and then over and then up. Okay, so there's a different trajectory that it might take, and that's because it's affected by the new particle that was added in. Now, if I forget about, which of these particles went there, actually that will correspond to a jump of a second-class particle. So the fact that under one configuration, the particle went to the right, and that under the other configuration, it didn't, represent the fact that actually the second-class particle, this particle, is being forced to move and switch spaces with it. So that's the explanation for a second class particle.
Okay, so
Now-
the statement, so the xt you've written here is a second class particle started from the position where you're adding a particle to get from.
That's right.
Eta
So
to
that would
zeta.
be, so if I assume that xt is a second class particle relative to the two first class particles that I circled here, then this would be the joint evolution. Yes. Okay, so what is an implication of this? Well, if we consider, I want to explain why we have this uniform -1, 1. So consider now at the hydrodynamic level, let's go back to the hydrodynamics. Let's consider studying hydrodynamic equation from two different initial data, both deterministic. One I'll call rho 1 union 2, which will represent it'll just be a step function at 0. And the other I'll call rho 1. Maybe I'll call that in red. And this will be a step function at minus delta. And so what I want you to think of this is going to represent first class particles, the asymptotic density, and this will represent first and second class particles. So what you should really have in mind microscopically is that I have, my particle system, and in one case I start with maybe from position minus delta over epsilon, I start with first class particles, and then from position 0, I start with a bunch of second class particles. So in the scaling limit, the density of first class particles will converge exactly to, the density of first and second class particles, if I lump them together, so collectively, will converge to this indicator function. And the density of just I think I've gone and screwed up the color scheme. But anyway, the density of just first class particles will correspond to this step function. Now, if I look at what I'll call rho 2, which should now just represent the density of second class particles, how does this difference evolve? So this should be equal to rho 1, 2 minus rho 1. And the question is, what does this look like? Well, it's easy because I know how to solve each one of these equations on their own. It's just a translation of the rarefaction fan. So if I draw these are my two initial datas. I had one initial data and then the other one was shifted by delta. So this is minus delta, this is 0. Then after some amount of time, well, what will happen is one of them will spread out like this, and the other one will spread out in very much the same way, but just shifted a little bit by delta to the side. And if I take the difference of the two, then what the difference will look like is basically, there'll be a little bit of a change at the boundary, but it will basically be something that's constant. So this is like, I don't know, t minus delta, this is t, this is minus t, and this is minus t minus delta, and the height will be delta over 2t. So the difference is this essentially uniform on the interval minus t to t. And now if you think about what that means microscopically, well, it's saying that the density of these second class particles, right? Because I know microscopically that my second class particles are just the difference of two configurations. And I know that each configuration is marginally converging into hydrodynamic limit to the evolution of the Inviscid-Burgers equation. So that's telling me that the evolution of this large mass of second class particles should converge to the difference of these two solutions. In other words, it should be uniform between minus t and t. And so if I looked at just a single particle, maybe the one at the origin, maybe just a randomly chosen one in this large mass, then its distribution normalized by t should be uniform on -1, 1. And that's what this is saying. Now, it's not saying that the first particle is, so it's certainly not proving the result at this point, but it's at least telling you intuitively that, typical particles, if I added a lot of second class particles, will behave uniformly in this rarefaction fan. Okay. So, not a proof. The proof is not so much harder, but at least an intuition for why. So this is kind of, sketchily suggesting the uniform -1, 1 result. So, one needs to put in some more work to actually prove that. Now, the next thing I want to explain is why almost sure is a reasonable expectation. And in fact, what's going on here is a similar thing. You use the hydrodynamic. So imagine that, actually, I see I'm running low on time. Let me switch. I have a version of the slides that I'm not going to need to write. So let me just go to the version that's already written. And this will save me a little bit of time. So, okay, so the idea for almost sure convergence is that imagine that you happen to be at a location, your second class particle happens to be along a certain velocity. I'll call that 1 - 2 rho. So in the rarefaction fan, we expect then that the local density will be rho. And by this local equilibrium heuristic, we expect that locally you'll see something that's like Bernoulli product measure rho. Now, Ferrari actually showed in 1992 that if you started out with that IID Bernoulli rho on the infinite line, then you have almost sure convergence of the second class particle to the characteristic velocity. And I'm not going to explain his proof, but I'll just explain to you why is it reasonable that this is true. In other words, why does, at least in expectation, why does xt maintain the velocity of the characteristic? And the idea is pretty simple. It's that if you're in this local Bernoulli configuration, you can ask, if you have a second class particle, the red particle here, you can ask, well, what is the probability, what's the rate at which it's going to take a jump to the left? And it will take the jump to the left under two different considerations. One is if it's forced to. So it will be forced to if there's a particle to its left that wants to jump, a first class particle that wants to jump. And that will happen at rate r, but only with probability rho, because there's only going to be a particle there with probability rho under this Bernoulli. On the other hand, with probability 1 - rho, there's a hole there, and the second class particle can take a jump to the left at rate L. Okay, so that's the sort of instantaneous rate of left jumps. And you can similarly compute the instantaneous rate of right jumps. And if you put them together, what you find is that the instantaneous velocity that the second class particle takes is exactly 1 - 2 rho. Now, this is not saying that it will necessarily go that way linearly, because this is kind of an expectation. And actually, it's not that easy to show the convergence almost sure, because you might say, well, okay, so look at it over a time interval 0, 1, and then 1, 2, and so on, and use the fact that these instantaneous velocities are independent, but things are not independent. Okay, so even though the expectations are staying constant, but things are not independent. In fact, this is why the lack of independence is why you end up with super diffusive fluctuations of the second class particle. Okay, so this is all the heuristic. And what I want to explain now is actually how to go beyond the heuristic. In other words, how to actually start to prove the theorem. And so what I'm going to do is I'm going to start by giving you a kind of a false proof, and then I'll tell you how you repair the false proof. Okay, so first of all, let me remind you that in the case of TASEP, which is what I'll talk about for the moment, this has already been proved by Mountford and Guiol, but by a very different method, and a method that will not generalize to ASEP. So the method I'll describe to you now will generalize, and I'll tell you how. So the first step in order to prove, so again, what we're trying to prove is that the second class particle started at the origin will converge divided by t almost surely to a limit. And then obviously we also want to know that it's uniform, but let me take that for given. Okay, so step one is to start with this step initial data, and with this second class particle at the origin, and run it till some large time s. Now, by hydrodynamic theory, we expect that the density will be this sort of rarefaction fan. It will be 1 to the left of minus s, 0 to the right, and then linear between. Now, of course, the particle configuration will not be exactly given by this density, but let's just close our eyes and imagine that actually, microscopically, the system at this time s is given by independent Bernoullis. So the occupation variables are independent Bernoulli with a profile of parameters that's exactly given by this hydrodynamic linear profile. Okay. And just again, let's assume that the second class particle happens to be at the origin. If it doesn't, then what I'm saying won't be so much harder, but it's just going to be simpler because then the characteristic is velocity 0. Okay, so this is a big assumption that you're kind of close to this local stationarity, local Bernoulli thing. But let's just imagine this is true for the moment. Okay, so now I want to explain to you if that were true, how would I get something about the motion of the second class particle? And so what I'm actually going to do is I'm going to imagine now augmenting my system. So initially I have a second class particle and it just happens to sit, right here, right in the middle, right? And now what I'm going to do is I'm going to augment it by adding in a bunch of second class particles in such again, a sort of a Bernoulli manner, in such a way as to increase the local density, say between minus s epsilon and 0, so that my hydrodynamic profile, my actual profile of the of the density, has a horizontal component that now it just goes to the right like this. Okay, so what I'm going to draw in these dotted lines. Okay, so I add a lot of particles to the left. Now, actually, from the perspective of the second class particle that started at the origin, it doesn't see the particles to its left because, well, it's TASEP. We're looking at TASEP and particles never look to their left. So certainly the second class particle at the origin is the king of all second class particles. It will not defer to those to its left. On the other hand, since we've added a lot of them in, we can ask under hydrodynamic theory, how does this large mass of particles evolve? Hydrodynamics tell us a lot about typical particles. It doesn't tell us much about individual particles. But what it will tell us is that this perturbation will evolve to a perturbation, but the evolution, which is now this solid red, which you can just read off from the Berger's equation, now lives between minus 2 epsilon s and 0. So if I run this up from time s to time 2s. And so what that's telling me is, well, most of the particles, most of the new second class particles will live to the right of minus 2 epsilon s. In particular, if most of them live to the right, then the one that I'm interested in, which is the one started off at the origin, will also live to the right of minus 2 epsilon s. So that's good because that tells us a sort of a lower bound on the motion of the second class particle. And actually, by using just particle hole duality, you can also get an upper bound. You can say that you're going to be less than 2 epsilon s as well. So you're going to kind of hem your particle in from the left and the right, obviously with high probability, assuming all of these sorts of things. And so it seems like we're making progress, right? Because then we can try to take epsilon to be arbitrarily close to 0. And we've gotten something about how much the particle can change in its motion, basically being forced to stay put. Okay, so that seems nice. So step 3, I'm going to tell you how to fix this. There are all sorts of problems in what I just said. For instance, I'll kind of start working backwards. For instance, if you look at this last argument that I said, which is that I run it between time s and 2s, and I get that it can at most change by epsilon s. Well, if I repeat this, so if I run now between 2s and 4s and 4s and 8s, each time I'll accrue an epsilon error, and these epsilons can add up and diverge. So unfortunately, I won't be able to really control things so nicely there. So what I'll need to do is do something more clever in order to really be able to do this. So I'll take actually a smaller scale than adding these epsilon intervals. I'm going to take an interval that's going to 0 relative to s. So I'll take some s to the minus gamma for some s to the 1 minus gamma. So rather than what I had called epsilon s, I'll take a slightly smaller scale and I'll work on that scale. And that will be enough to be able to show that the kind of net contribution is actually going to 0 and not kind of diverging. The other thing, another problem that can occur is that this argument is only going to control me between times, s, 2s, 4s, 8s. I need to control wiggles, how much the second class particle can move in between. And in order to do that, I can use some brutal Poissonian bounds. But those brutal Poissonian bounds are too brutal to allow for this sort of exponential growing time scale. So actually what's more natural is to choose a time scale where you go not quite at exponential growth, something like e to the square root of m or n. growth. And then once I do that, I'm able to control with some Poissonian bounds the intermediate behavior. Now, the real problem, so these are kind of minor fixes. The hardest part, though it certainly can be done, is to justify all of these hydrodynamic approximations, right? Because what I did in the beginning is I said, imagine that I had a Bernoulli system, but obviously I don't have a Bernoulli system. And so I need to justify that I'm close to one on some scale, in particular on the scales that go into the second step. I had this augmentation. And then I'll use hydrodynamics a second time, which is that after I do this perturbation and I run it for an additional amount of time, I need to know that my actual particle configuration is close to the hydrodynamic evolution and close in some small, some scale that's actually shrinking, that's not in the hydrodynamic scale. So something smaller than the order S hydrodynamic scale. And so for this, what I really need is something that's called an effective hydrodynamic concentration result, which is saying that I can control the number of particles that live on smaller intervals than the size of the hydrodynamic limit, and with better precision than hydrodynamics give me, and with some exponential tails. So, this is just an example of the type of result, and the ability to prove this type of result is very much relying on exact formulas. Okay, I'm not going to go into the details, but once you have these, then you can establish with various couplings, you can establish the result that I claimed for TASEP. So in the last, say, 2 minutes, I want to just explain to you what happens when you take L bigger than 0. And the first thing is that you throw your hands up in the air and you say, crap, when I have ASEP, the first particle, I did this augmentation process, right? I added a bunch of second-class particles behind me, behind the initial second-class particle. And in TASEP, I knew that the second-class particle that started at the origin was going to be the biggest of all of them. In ASEP, that's no longer true, right? Because adding particles behind you actually increases the speed of the second-class particle that's at the origin. When I add particles behind, it means the second-class particle can't jump backwards as often. And so it actually moves forward faster. And so this is a problem because it means that the actual evolution of the second-class particle I care about is going to be less than the thing that I know how to control, at least if I naively apply the same argument from before. However, there's something that comes to our saving, which is a coupling that Fredo and Rezakhanlou introduced in 1995 that says that, well, if I do this process of adding a bunch of second-class particles behind me, it's true in ASEP, I'm not going to necessarily stay ahead of them if I'm the first second-class particle. However, he showed that stochastically, I'll stay ahead of a randomly chosen one of these additional second-class particles. So if I add 100 extra second-class particles, so that now there's 101 in total, if I just look at the evolution of, I uniformly choose one of them at random and I look at that evolution, the distribution of, over both the randomness of the evolution and the randomness of the one I chose in the beginning will be stochastically dominated by that of xt. So in other words, if I can control where most of the particles live, I can still control the distribution of xt. And so from that, I can still use the hydrodynamic argument, or the sort of effective hydrodynamic argument I was explaining before, to control the evolution of xt between consecutive scales and the wiggling. The only thing that I need in addition is I need these effective versions of hydrodynamic results for ASEP, and these were not in the literature, and so there's a lot of work needed in proving them. And I won't go into it, but I'll say that these rely on exact formulas of various types. Okay, so let me just conclude because I think time has elapsed. So I sought to prove a strong law of large numbers for the xt of t, xt over t, the evolution of the second-class particle, and construct this ASEP process. And the technique that we use is one that is very much rooted in the particle system itself. So it doesn't go through any couplings to auxiliary systems. And so it's actually something that would be amenable to much, to other processes, provided that you have some version of this effective hydrodynamic results and this coupling. So an example where this should work, and I think it'd be interesting to work out, is the stochastic 6-vertex model. And an example of something that's a scaling limit of ASEP, which would be interesting to probe, is the KPZ equation. So these are interesting questions. There are other questions. So for instance, the properties of the ASEP speed process or the fluctuations of the second-class particle around its terminal velocity. And these are questions that now are, at least in focus. The other point of the talk was to just give you a little bit of a flavor of the interplay between what you can get from couplings, from from probabilistic methods, and exact formulas. The ability to prove these sorts of effective hydrodynamic bounds. And so I think that I think this is a place where I'll stop and just say that I don't know how to prove a result of this type without this. And so I'm very glad that we were able to put them together. All right, thank you very much.
All right, so